All right, howdy everybody. Um, who here likes assemblers and disassemblers? Okay, who here has written an assembler but not a disassembler? Okay, I got two hands or so up. You folks are psychopaths. And how many, even as just a toy, even as just to solve one specific problem, have written a disassembler but not an assembler? Okay, a hell of a lot more hands. In this lecture, I'm going to be talking about an assembler that I've been writing lately. I've been doing it for microcontroller reverse engineering, which has quite different constraints from what you would have in the x86 and ARM64 worlds. But I think that many of those ideas are worth porting back to our desktop environments, because our disassemblers have gotten a hell of a lot better over the past 30 years. We have lifters, we have decompilers, we have all of this fancy static analysis stuff, and our assemblers have not gotten much better. There's no reason for these two things to be decoupled. I think that the right way to make a disassembler is through the exact same definition as the assembler, so that at the end of your project, you have a tool that operates in both directions for every instruction that you've defined without exception. And when you do it this way, you can do a lot of crazy stuff like self-testing. Because when you're writing an assembler, you screw up. You copy and paste similar instructions, and accidentally they're equal, or accidentally you convert a bit mask wrong or something, and you don't realize it until much later in your project after it's caused you pain. And particularly in the embedded world, when people are working on exploits for 8-bit machines, we have this bad habit of not having an assembler and not having time to write one. So we just start writing machine code by hand using the paper documentation and the .b directive in NetWide assembler. And this is quite bad. So the other thing that you'd like to have is to be able to add support for a new machine language in a couple of hours, so that you can take a quick break from your project and then get back to it, rather than needing to invest a lot of work in adding the language when you'll say to hell with it and write your machine code by hand just to keep moving. So you might know me from the International Journal of Proof of Concept, or Get the Fuck Out. We've distributed that on paper here at Recon a couple of times. You might know me from a project called ROM tool, which is a CAD GUI for reverse engineering photographs of ROMs into logically ordered bytes that you can disassemble. Half of the motivation for the assembler in this lecture was for ROM tool to be able to identify when it had correctly ordered the translation of bits from the physical order to the logical order. It's easy for the tool to enumerate it. In order to actually find the right one, you have to write a Yarrow rule or use a disassembler that can recognize which solutions might be right. I also have a book out, Microcontroller Exploits, from No Starch Press. We might have a paper copy or two later this weekend. You can grab it from Penguin Random House, wherever fine books are sold. As you read it, please remember that the book came before this assembler, so the off by 2 error in the smart card exploit chapter is something that I could have avoided if I had this tool available. All right, this is what you might have as a mask ROM. This particular ROM is from the CPU of the Nintendo Game Boy. Show of hands if you've ever played a Game Boy. Okay, and when your asshole brother steals your Game Boy cartridge and you only have the Game Boy itself, and you turn it on, instead of the Nintendo logo coming in from the top of the screen, you see a black bar. And the reason why is that the cartridge contains a copy of the Nintendo logo, and the boot ROM shows the logo from the cartridge, whatever it might be, on the screen, and it slides it down and it does a little animation and it jumps into the game. But it only does the animation and jumps into the game if the logo is the Nintendo logo. This allowed them to use trademark law to protect their cartridges, so they did not need a lockout chip like earlier Nintendo platforms. And this ROM is the program that does it. If we zoom in a little, we can actually see the ones on the zeros. In Mask-ROM tool, you draw lines through these. Horizontal lines for the rows, vertical lines for the columns. Wherever they cross, those are bits. And the bits can be determined by the color, sampled in a couple of different ways. Usually, you're looking at one of the color channels, and you're either looking at just that point or a thin vertical or horizontal stretch. All of those different modes are supported. If your chip is weird and you need a different type, it's easy to add that through C++ class inheritance. And at the end of that, you get the bits in logical order. You get the bits in physical order. And the difference between physical and logical order is very important. Logical order for a natural language is in time. As I'm speaking each word to you, they come after each other in time. Logical order for a written language, well, physical order for a written language can vary. In English, we go left to right. In many Semitic languages, you go right to left. On a microchip, you can go in any physical order that allows the chip to function. So the general rule is that the bits of significance are separated. You have all of the most significant bits on the far left, or you have them all on the far right. And the least significant bits will be on the opposite one. And sometimes you step left to right, sometimes right to left, sometimes you do rows before columns, sometimes columns before rows. There are many different ways in which you might enumerate it. And if you get them right, then you get to read out the code. This is the start of the Game Boy boot ROM. Can anyone tell me from the instruction at address 0, this is an SM83, which is similar to a Z80, what does that very first instruction do? And why does it do it? Yell out the answer. You got to yell loud. Right, sets the stack pointer. Why does it set the stack pointer first? I can't hear. You got to yell it. Right, the stack pointer is not initialized in hardware, so you have to set that pointer first in order to begin making function calls. Because the stack pointer is not set in hardware, as an ARM Cortex chip might do, where it loads it from the interrupt table, because it's not set in hardware, every program for this architecture begins by setting the stack pointer. So that becomes a rule that we can look for. We can say that for any architecture remotely like Z80, the very first instruction will be a load where the destination is the stack pointer. Doing rules like that allow us to search through many different potential decodings and skip over the ones that are wrong. If I look for only the decodings in which 31 is the first byte, I get 3 potential decodings with my software, maybe 6 by now. And one of those is right, and as a human reverse engineer, I can run through 6 potential matches very quickly to find the true one. Going back to assemblers, IDA Pro, Ghidra, Radar 2, Binary Ninja, these things are amazing. They allow us to work on very large projects, obscenely large. They allow us to migrate symbols between different versions of our projects. So we reverse engineer one, but we get the results for a dozen different versions. They support a lot of different architectures. They have lifters and they have decompilers. They have all this crazy stuff. On the assembler end, we hardly have anything. We have NASM, which is great, but only works for x86. We have Nakan assembly, which works for many different languages, but is easy to make mistakes when you're adding architectures to. And we have macro assemblers, which are easy to add new languages to, but terribly hard to do it accurately. And terribly hard to extend if you have something weird, like anything that was not anticipated at the time that the macro assembler was designed, because these are working by sort of like C preprocessor definitions. One thing that they're great at, though, is having a command line that you can script, that you can make commented assembly code that then becomes your project. And all of the disassembler maintainers in this room, whether you work for Hexrays or for whether you tinker on Ghidra or work for Binary Ninja, I'd really love it if you would add a full-fledged assembler to your architecture if you were to take any one thing out of this lecture. Like, please steal that feature, because I'd love it if my Binary Ninja license also included the ability to write programs in the languages that I'm reverse engineering. So my assembler is ridiculously easy to retarget. You have a C++ class, you inherit from that, and then you just start naming your registers so it knows that they're not symbol names. And then you start throwing in new instructions. When you throw in those instructions, you are defining both the machine code and the assembly language at the same time. You basically do this by having bit masks to describe each field, and you insert these fields in the order that they would appear within the assembly instruction. For things like groups, you just have a group field and it has members, and you can nest that however deep you like. It has a shared parser for all languages. So at no point when you are adding a new language do you have to mess with the parsing code. And this also means that down the line, when I get around to writing a better parser, I can gut the original and replace it without having to touch things up in each language individually. I should be able to replace all of them with a better parser at the same time. It has multiple interfaces. The first, which is the one I'm using in my mask ROM reversing tool, is a C++ library. In this case, I'm providing it with a particular potential decoding image, and I'm asking it either for the assembly language or for the likelihood that it exists as a program in my known language. There's also a command line tool, which I use for disassembling a potential binary or assembling source code into a binary. And there's a REPL interface, because quite often when I'm writing support for a new language, I'm also trying to learn that language myself. And in the same way that when you're trying to learn a native language, it helps to have like a buddy who speaks it that you can text, or Google Translate to just make sure that you're not completely messing up a conjugation. It really helps to have that REPL interface so that I can type in an instruction and get back the bytes of it, or type in bytes and see what that would have assembled to. And it exports to commented bytes. So a big mistake that many of us learned from the C++, from the C preprocessor, is that we throw away comments. In this tool, the comments are never thrown away, so that I can include them in the output format if the output format supports it. We'll see a couple examples of that in a bit. And it's fully integrated into mask ROM tool for reverse engineering. So in addition to, say, MAME's GoodASM or Radara 2, you can also have it run to my disassembler for any of the languages that have been added. We'll begin with a quick example. I was visiting Sergey Bratis at Dartmouth. We were talking about exploit writing and cool tricks from the past. And I started telling the students about the TI-85. When I was a kid, laptops were expensive, palm tops were useless, and smartphones didn't exist yet. So we had graphing calculators. And these graphing calculators ran a dialect of BASIC. The dialect was not a particularly good one, but it was better than nothing. If you suffered through it in a few weeks of math class as a 7th grader, you could figure out how to write a snake game or something like that. There were some students who were a bit more clever than that, though. These 90s teenagers figured out that you could back up all of the RAM from this calculator. Back it up to your computer, and you could change things in it. One of the things that you could change were the custom menu entries. And a menu entry in this calculator is an ASCII string followed by a function pointer, the function pointer for the handler to the menu entry. Well, when you back this up, you can replace that function pointer with anything that you like. So they figured out that they could replace it with the address of native machine code and then execute that code on the Z80 CPU in order to get code execution, which is great. But they had a problem, which is that they'd really like to have BASIC continue to work. And BASIC uses a heap for all of its variables, and that heap is garbage collected. So they needed to find some place in memory that would never move, that would always be in the same location. And what they did was they executed the LCD screen buffer, because that is in hardware and it's always at the same location. And they would put a little bit of code there that would find their position-independent code anywhere else in memory it might be, and execute it from that location. And I wanted to toy around with this, but I did not have a good Z80 assembler. And the public tools available for it were left over from the 90s. They were awkward to work with. So on the bus to Logan Airport, I started writing a Z80 plugin. In ByAssembler, you begin by calling the insert method on a created mnemonic. The mnemonic is a class. The parameters of mnemonic, first we're giving it a string that says nop. That's the name of this instruction. The 1 means this is 1 byte long. Then I have strings for the value and for the mask. 00 means that 0 is the data value of this instruction. And FF means that every bit of that byte is meaningful. This is the long and generic way to say that any 00 byte is a nop. I also provide it with a help string. This is used for like a cheat sheet, so that on every language that I've created, I've got a cheat sheet that explains all of the different instruction forms and where the memory is coming from, which is very handy in that some of these have their arguments in the reverse order. Some of these require the accumulator as a parameter, while others have it implied. And then I have an example instruction, which is used for my self-testing. So nop had better assemble to this and then disassemble back to that same string. After I've created this, I immediately have that one instruction working, and I have it working both from the command line and from the REPL. So in the REPL, if I type in nop, I get my 00 nop, and the same thing if I give it 00. And of course, a real-world instruction has a parameter. On most CISC instruction sets, your parameters are of a few particular types. Like you'll have a register that is 1 of 8, or you'll have a register that's 1 of 16. So I define that by inheriting a class and then instantiating it. And this is a decrement of any 8-bit register. On line 764, I'm defining that 38 is the mask for that particular register. And on line 761, I've defined that C7 is the mask for the opcode. And there are self-tests that run on all of this. So dec B had better match this as an instruction in disassembly and then also as bytes in assembly. The bitwise OR of all of the masks had better be all Fs. I can define a don't care field. I can explicitly say that some bits are not used, but I have to do that explicitly, and I cannot simply leave it undefined because that would imply a mistake. And then the end result of this is that I've got all of my decrement instructions. And by building up the instruction set like this, going page by page through the manual, in an hour or two, you have the complete Z80 language implemented. There are a couple of tricky parts to this. How many of you do 32-bit ARM? Okay, 32-bit ARM has this really annoying thing where when your registers are 15, the instruction means something else. Z80 has a similar thing in that it has the HL register, which fits in the place of what would be an 8-bit register, creating an exception to your definition. And the way that we handle that is by this prioritize call on line 73. That simply says that if there's a disagreement between two different instruction definitions, we want the latter. You can also give it a numeric priority if your language is cursed enough that it needs more than one level of prioritization. And the self-test will recognize if there's ambiguity because of an undefined priority. Having implemented that, I mean, we're really talking 2 hours on a bus here. I could then start writing programs for the TI-85, and I could begin writing them on my modern machine in Emacs, assembling them and running them on the calculator. Having your assembly code is great, and having it in your Git repo, you get to feel all good and stuff, but you actually have to deploy that to make it useful. And a lot of us also write exploits for these things, and when you're writing exploits, you need to deploy them from some other code. So it's not necessarily just making an executable, it's making an executable that I trick another process into running. So a binary output file is fine for a regular executable. I also want an assembly listing for making sure that my bytes look right, or for debugging. This has all of the bytes of my output along with my instructions and my original comments so that I can understand what each byte of my code is doing and make sure that it looks right. Now, I have my assembler, and I think that my assembler is easy to compile, and I have pre-compiled versions available for Windows and for Mac, but some of you might use VAX or something and not have access to my tooling. So I would like to be able to share my code with you so that you can work on it without having the same tool. And for that, I have it output net-wide assembler code, complete with my original assembly language and my original comments, so that if I give you this file, you can make small changes to it. If you see a constant that looks wrong to you, you can alter that, reassemble it without having any of my tools, and continue going. I was writing a smart card exploit for the Nagra ROM 3 card. This was released in 1998. It was the subject of the EchoStar NDS lawsuit, in that NDS had written an exploit against this card, a few of them actually. So I wrote my own, and I wrote my own using a modern USB smart card reader. And a USB smart card reader has different rules from the old serial port ones. On a USB one, you are not allowed to receive a message from the card unless it is grammatically correct, like of the appropriate length and with the appropriate checksums. So I wrote a Golang program and shellcode and an exploit and all that stuff of my own in order to fit this more modern protocol. And when I wrote that in assembly, I wanted to deploy it to the card. So I added support for the output format of Golang byte arrays along with a hash map of the symbols. And again, you keep all of the comments with the code, so you're able to make any changes you like. By having the symbols, you're also able to patch the code however you need to. In the case of my smart card exploit, I had a magic constant for the address that I was reading data from. And I needed to change that magic constant. By having the symbol available to Go, as I change my code, that constant automatically moves within the Go code. I've been playing with other old smart cards. They're great for mask ROMs as well as for old exploits, because you can get the old exploit, but very little documentation on how it works, disassemble it, and have like the way that some people do Sudoku. This particular card, the NDS-F card, is 6805, except that the opcode byte is scrambled. 6805 has a single byte opcode, and it is always the very first byte. The parameters are not scrambled. So if you have an instruction, on any given instruction, the first byte looks different, all of the remaining bytes are the same. And if a byte is ever, that of an instruction is ever read as data, it is also unscrambled. So Chris Gerlinski, is he here this year? It's a shame. He's a great guy. I wish he were here, because at Recon a few years ago, he nerd sniped me with a few of these things, and that's how I got stuck into it. He sent me a tweet with a quote from a 1995 mailing list post describing the scrambling on this chip. He says, "Only the opcodes are scrambled, not the operands. The bit order from most significant bit to least is 764-53012. And then you flip the most significant bit." And he pointed out that you could see this in the dive photos. So this is my implementation of the scrambling in my FCard module. All I'm doing here is I'm subclassing the 6805 language support, and then I'm adding a function to do the scrambling. And you'll note that the scrambling here is symmetric, so if you do it twice, you get back to the beginning. I then followed his instructions to find this within the die. This region in the middle toward the left is where the scrambling actually happens. If you look closely, you have yellow horizontal lines, and you have orange vertical lines. And the vertical lines are in polysilicon, while the horizontal lines are in metal. You can visualize them. So the most significant bit is on the far left. The least significant bit is on the far right. This is an 8-bit chip, so we're doing 8 bits at a time. And these are the columns that go into the instruction decoder. You also have the rows. In the rows, the least significant bit is at the top. The most significant bit is at the bottom. And then you have vias. You have these little these little vertical connections between the polysilicon and the metal. And that's how the scrambling occurs. When they manufactured this chip, they have masks for each layer. One of the masks is the one that creates vertical connections in the via layer. And the via layer is the only layer that is different between the commercial version of the chip and the smart card version of the chip. And why would they do the scrambling in the via layer rather than other layers? Somebody yell out the answer. He says it's cheaper to change, which is almost but not quite true. The real reason is that the via layer is also where they're encoding bits of the mask ROM. So this means that they can have a different scrambling for every customer individually. And if you were to get the same smart card chip from a different satellite TV company, it would not follow the same scrambling routine. Chris then sent me a little exploit for this card. He says that you send a 5-byte command, you receive a 1-byte acknowledgement, and then you send this 92-byte payload, and you'll receive a copy of the 3-kilobyte EEPROM. The reason why they were so obsessed back then with getting the EEPROM out is that many of these smart cards had no ASIC encryption. And if you were able to get a dump of the mask ROM and also of the EEPROM, you could emulate the card, and the receiver could not tell the difference. And by sharing the EEPROM, you could then have 1,000 people receiving television using a single subscription, which was how they made money off of this stuff. So I dump that code into my disassembler, and I get back the disassembly. And we're going to play another game here. There are 3 things in this disassembly that tell me that this is real code and not bullshit that I misdecoded. What are those 3 things? Yell out stuff. What do you see here? Why is this real? Compare in the branch. Give me line numbers. 7 to 9. Okay. So at address 7, we have a compare of the accumulator to the literal number 11 hex. And then we have a branch not equal on that comparison. In real code, you have a comparison just before a branch. And in randomized code, you'll have separations between them, and it won't make much sense. What's another thing that you see here? What do you see? Consistent addresses. All right. What are my addresses there? 88 on line 2 and line 5. So we have a global value, and we're reading that value into the accumulator. We're then incrementing it, and then we're writing it back. That is classic loop iteration. And then the most significant thing are these no-ops. It is normal in an exploit to have an op sled in order to give yourself some spacing. I also noticed that the subroutines are all within the same region of memory. And if you had the memory layout for this chip, you would see that that is within mask ROM. as the exploit is reusing portions of the mask ROM in order to communicate with the outside world. This is particularly handy because mask ROM is like the total extreme opposite of address space layout randomization. None of that can possibly change. And the only exception is in more modern chips where you're able to override individual words, such as with ARM in the patch breakpoint unit. And then, of course, the iteration on the global variable at 88 hex in this loop tells us that this is real code. I can then convert that into my own assembly code. I can then load that into my own like Golang smart card exploit tool. We have some other problems that this tool can help with. We have what's called the bit ordering problem. So one fetch from the mask ROM is a fetch of the word in the native size of the ROM. Usually this is the same as the fetch size of the CPU. There are a couple of cases where the CPU has multiple fetch sizes. So generally on an 8 chip, we're going to have an 8-bit fetch. On an ARM chip, we're going to have a 32-bit fetch. Some don't match up. Like the PIC16 has 13-bit ROM words, even though it has 12-bit instruction words. And I think the reason for that is that they didn't have a 12-bit ROM IP available, so they just copied a 13-bit one from an older chip. Usually you'll have the most significant bit on one side, least significant bit on the other. Sometimes they're interleaved and you'll change directions halfway through. Like one row will go right to left and the next left to right. Does anyone here remember the Clipper chip from like 1996, 1997? Okay, a few hands are coming up. This was during the Clinton administration. It was key escrow cryptography. So the idea was that the US government would give you an encryption device, but they would keep the backdoor database to it. And if there were ever a warrant against you, they would be able to decrypt your phone calls. I've been reverse engineering that chip since grad school. Matt Blaze nerd sniped to be with it. And this is the mask ROM from that chip, specifically the second generation, the MYK82. It was in a PCMCIA card. You'd plug that into your phone or into your laptop. You can encrypt your email with it, your phone calls. And I've since dumped the ROM from it, which is encoded in the in one of the lower layers. So you need to first decap the chip with nitric acid and then delayer it with hydrofluoric acid. When all of the row and the column lines fall off, you then wind up with the exposed bits. Here are all of the exposed bits. This is a 32-bit ROM. If you count, you'll see that there are 16 major columns of bits here. Each of those is divided in half, with the right side being the one bit of significance and the left side being the lesser bit of significance. With my software, I can mark up all of these bits. There are about 100,000 of them that are used. If we zoom in here, and in my software, I select like the first instruction word, and I ask for it to be highlighted, you can see that within each of the bits of significance, which is half of a major column, and you'll see here that's like 2 groups of 8-bit columns. The first bit is the one in the upper right. And I wasted a week in Bogota with pen and paper to figure out that the ordering from there is that you move one to the left until you hit the end of the space, and then you drop down and move back to the right. I also figured out that the most significant bit is at the far right of the chip, and the least significant bit is at the far left. If I jump back one, the way that I figured out that the program began at the top of this image is that at the bottom, it all becomes the same. This program ends with all zeros. And the way that I figured out that it began with the most significant bit at the far right is by looking and seeing that the far right is a little fainter for a column and a half, and then it gets dark for that third one. The reason why it does that is from the ARM instruction set. This is an ARM6, which is the predecessor to ARM7 TDMI. They're pretty much the same, except that ARM7 TDMI, I think, added like unaligned instructions and optionally thumb 1, neither of which exist here. So these are all 32-bit instructions. The most significant field in every instruction, not just the branch and exchange, in every instruction, is the condition code. So for those of you who reverse engineer 32-bit ARM code, what does each 32-bit word begin with? E. Why does it begin with E? E means always execute it. And if we zoom in a bit, we can actually see the E here in whether it is faint or dark. So we have faint, 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 dark. That is 1, 1, 1, 0. That is the E. That gets us halfway there. That tells us the bit order within a word. That does not tell us the word order within the row, or whether rows come before columns or columns come before rows. This is a potential decoding, and you can see the E's there. There is only one instruction in that entire sequence that does not begin with an E. It is like a clear majority of the whole program that instructions will be unconditionally executed rather than conditionally executed. And the ones that don't begin with an E probably follow some sort of a comparison. In 32-bit ARM code, you have this exclamation point that means that you're not writing the condition back. That will probably not come before an instruction one. And I say probably here because there are exceptions to all of these rules. And sometimes we have data mixed in with our code. But it's handy for the assembler to be able to understand these rules in order to speed up the problem of figuring out the ordering of the bits. Now, the bit ordering solution, easy on ARM. We look for the most significant bit. Each language needs a different one. In CISC languages, we have many words per instruction. Remember, the word is the native size. The word is like a byte. If I have a 3-byte instruction, that's 3 words. That's 3 separate positions in the table, and the bit ordering often cannot be done separate from the whole instruction ordering. In some languages like 8051, it's really difficult to do this based upon the legality of the instruction. Who knows how many opcodes are defined in 8051? 255 opcodes are defined out of 256. Only A5 is undefined. And that meant that every non-standard 8051 added A5 as its extra special instruction, like a software breakpoint or something. So we want to solve for the word order. We need to figure out whether the words come left to right to left, whether we're interleaving or not. On RISC, we got the jumping ahead here. These are 2 potential ARM programs. One of them is right, one of them is wrong. I want you to quietly read it until I count down from 5, 4, 3, 2, 1. Yell out in unison if you know it. Which one of these is correct and which one of these is bullshit? Which is correct? The right. Why is the right one correct while the left one is bullshit? This is the very beginning of an ARM program. It's an antique ARM program. Interrupt vector table, exactly. These days, ARM likes to use addresses in its interrupt table. Back in the ARM6 days, it used instructions. And the first 8 instructions were branches to interrupt handlers. They should all come in order at the beginning. And in an ARM6 chip, if you're trying to recover the boot ROM, it really is sufficient for you to know that the program probably begins most words with an E, and that the first 8 words will probably be unconditional branches to specific addresses. On Z80, you're not able to do that because Z80 varies a lot. and your instructions span more than one word. But you can look at other features of Z80. Z80 has these things called DD instructions. In CISC instruction sets, you begin with your opcode at the beginning of the instruction. Sometimes you run out. 8051 uses up almost all of the opcodes specifically to prevent feature creep. Z80 wasn't smart enough to do that, so Z80 wound up with the DD instructions that have a 2-byte opcode instead of 1. So a good way to identify that Z80 code is in the proper order, meaning that not only are my bits in the right order, but also my bytes are in the right order, is to do a linear disassembly of the whole program and look at everything that begins with DD. Compare the ratio of those that are valid instructions to those that are invalid instructions. Put differently, if I have a potential instruction and it has a multi-byte opcode, is it legal? Using that, you can reliably identify Z80 code, and because the different 8080 variants, like SM83 or 8080, do not use the same DD secondary opcode list, you can also distinguish between the similar languages. Final feature we need is bit damage. This is something that you never have to deal with in the software world, and in the embedded world, you have to deal with all the time. When I am reverse engineering a mask ROM, I am a human being with a chemistry lab built in an unused kitchen, and I make mistakes. Sometimes my house wiggles a little bit. I'm not that far from the highway. Old wood construction, when that wiggle happens, I sometimes get a blurry frame, which confuses the stitching of my software. I'm a bad lab chemist. I kind of do it like cooking, and sometimes I screw up. Sometimes there's a little bubble on top of the chip, and nothing within the bubble renders correctly. An assembler should be able to keep track of those damaged bits, because I usually know their location, even though I don't know their value. And I would like that location to carry through from my physically ordered bits into my disassembly. It's also the case that because we're grouping bits of significance, even if I have a large region of damage, all of those damaged bits are probably spread out, and I only have maybe one per instruction, or at least one per opcode, which means that looking at my assembly code, I might be able to figure out which of the two options is correct and which of the two options is not, and through that recover the bits that have been damaged without having to go back for another chemistry pass. Here's an example of what damage looks like. Here we have a mask ROM from, I think, a 90s smart card, and we have just a little bit of lint on the chip. This could be cleaned off, others could not. After I mark my bits up, I mark the damaged ones as well. So all of these that are surrounded in cyan are damaged bits that are not to be trusted. The rest of the bits are correct. Here's more serious damage. This is from a Tamagotchi Game Boy toy. It was a Japanese toy that the killer feature is that it would beep in the middle of the night to wake your child up. For some reason, it never made it to the West. I know some parents who think that it was attempted as retribution for World War II. When I zoom in here and I've got my disassembly, and the disassembly here might be in the wrong order, so don't pay attention to the individual instructions. My disassembler for this tool has the option of showing me the damage mask rather than the data bits, so that when I look through these different instructions, I know which ones of them I should trust and which ones of them I should not. With a bit more work, it would not be hard to make like a drop-down menu so that you could choose between the different values allowed by the damaged bits, at least when there are a few of them. These sorts of tricks, having embarrassingly easy retargetability so that you can add a new language in a couple of hours at a coffee shop and then get back to your project. Being able to detect mistakes in that definition generically, so that you can very quickly find when you fat-fingered a mask or an offset. Being able to create both an assembler and a disassembler at the same time without having to make separate definitions and hope that they're equal. And being able to export into other convenient file formats like Golang or C source code for use in other tools. And recognizing damage, maybe less so recognizing damage. But those first 4 features would be very handy in desktop reverse engineering software of server class 64-bit machines. And I would very much like if a year from now, those sorts of features existed in IDA and Binary Ninja and the other tools. And if you could also have damage, then I could stop writing my assembler and go back to using your fine tools. And I would enjoy that very much. If you'd like to follow further adventures here, I've got a couple of projects on my GitHub. Mask-ROM tool is my GUI for taking a photograph of a chip and working my way backward to the logically ordered bytes. GoodASM is my assembler and my disassembler and the C++ library for the same. And there are even smartphone apps now. If you want to do a TikTok interpretive dance of reverse engineering, that would be the way to do it. Nipper tool is my modern exploit for the old Dish Network cards. If you want to buy a couple of those on eBay, plug it into a USB smart card adapter and start running your own 6805 shellcode. It's quite easy to patch. And GB-ROM tutorial is a photograph of the Game Boy ROM that you begin with the photograph, and by the end of the tutorial, you have all of the bits and you've validated the checksum, and you can then read the assembly code that started your Game Boy when you were a child. And Microcontroller Exploits is a book that I recently published through No Starch Press describing these sorts of tricks for extracting memory from locked microcontrollers where you're not supposed to read them, but you want to read them anyways. And that's all I got for you today. Thank you kindly. Right. I think we have time for just a few questions before lunch. If you could grab the microphone, wave your hand like you're having a seizure or something. Oh, yes. Oh, well, he's going to go first, and then the microphone's going to come to you over here.
So does your disassembler come up with metrics for how likely a disassembly is to be correct using these sorts of heuristics?
So I tried doing the training and heuristic style, and I found that it wasn't very effective because it required a large training set, which I don't have for these architectures. Many of these that I used in the lecture are more popular languages, but I also support languages like TLCS 4.7, which I've never once seen a real program for. I only have the documentation and photographs of the chips. So eventually I came to the conclusion that it's better to write a hard rule for a particular language than trying to make a generic heuristic, like the number of valid opcodes to invalid, that could vary dramatically between a language like 6805 that uses rather few opcodes and a language like 8051 that uses all of the opcodes.
Okay, but you do get some kind of metric out for even the manually coded, is this good or not?
Yeah.
Thank you.
Linear scale and also yes or no for the threshold. So I think there's a question over here. If you could raise your hand so that we can find you with the mic, or... Oh, sorry. Yes.
Thanks for this awesome talk. Could you please describe your microscopy setup a little bit?
My what setup?
Microscopy.
Certainly. Could you move the microphone to him as I answer this question? So the first stage of this is through a chemistry lab. I use red fuming nitric acid to boil the packaging off of a chip, and then I use 20% nitric acid to burn the bond wires off of the chip. It's kind of counterintuitive, but the weaker your acid, the more it attacks metals, and the stronger your acid, the more it attacks plastic. After the bond wires are off on some chips with a metal via ROM, I can see the bits from the surface. On others, I need to remove the upper layers, and I do that with hydrofluoric acid under heat. By the time the hydrofluoric acid has taken a layer off, that exposes the ROMs of many chips. Not quite all of them. The third type is called an ion implant ROM, and for those, I need to use a cocktail of acetic acid, nitric acid, and hydrofluoric acid under ultraviolet light, and it has a yield of about 20%. And that's 20% to get any of the bits, many of which will be damaged. So in that third type, the damage recognition is most important. And then I clean it off with acetone and isopropyl alcohol and put it on a motorized stage in which a robot microscope that John McMaster made steps across the stage and gives me 100 or 1,000 photographs, all of which get stitched together into a panorama. And that panorama photograph is the one that I'm actually recovering the bits from. Yes?
Just kind of piggybacking off of that, do you have any pictures of or videos of your kitchen process?
I
Definitely
do.
Curious.
I have a lecture from B-Sides Knoxville a couple of years back in which I walk through the chemical processes. I've refined it a bit since then and might make a good Recon lecture for next year. Or, if we could find the chemicals well in advance, we could do a workshop on the terrace and hope that the hotel doesn't ban us for life. All right, I think that's it. Thank you all kindly for your time and attention.